Okay, so we got the recording going. Yesterday we finished off by talking about areas, and so hopefully that was a little bit of a break from some of the more complicated things. Of course, within these area problems, all the techniques of integration still apply. At least at the moment, a lot of these problems we're not going to fully work through. The real practice right now is setting them up. So we're getting into areas and volumes, and it's a much more geometric concept. And so the biggest thing we want to practice is using our visual spatial skills and setting up these integrals, like writing the correct integral that represents the volume or the area that we're trying to find. Once the integral is then set up, of course, we have all of the techniques of integration under our belt to approach those. So I probably won't finish a lot of those since we've just finished up doing all those techniques of integration. If any of them are complicated, or if any of them you guys think we want to work through, let me know and we can work through it. But yeah, for now, want to practice the geometry, the graphing, and the visualizing, and all of that. So let's start off with areas. Areas, again, fair game for the quiz, or sorry, for the midterm on Monday. And then volumes are going to be on the next midterm. So volumes we won't actually have on the Monday's midterm. But areas, this topic does lead us directly into finding volumes of solids. So let's take a look at doing a few warm-up examples. We saw a couple examples, just two yesterday, of areas where we wanted to do one integrated with dx, the other one integrated with respect to dy. And so I wanted to do a couple more examples to just see the types of things that might come up. So our first example, I've got this BDD, I mean bounded. So we want the area bounded by the x-axis. So y equals 0, y equals square root of x, and y equals 6 minus x. And we wrote down our steps yesterday. Remember, step one, in pretty much any word problem or any visual problem, draw a graph, draw a picture. So first thing we want to do is draw a graph of these guys. We know we're bounded by y equals 0, and specifically these graphs are positive, so we're going to be above the x-axis. So I'm just going to draw the vertical side of our plane. We've got y equals 0, of course, the x-axis, and then square root of x. It's going to look something like that. And then 6 minus x, a basic line. So, of course, at the moment, it's a little hard to see. But, always read the problem carefully. It could be this area over here, could be this area over here. And since we're bounded by the x-axis, we've got this line, that curve, and that curve. So we want this area down here. And how do we set this up integral? How do we set this integral up? Our step 2 is to find the intersection points. So let's go ahead and do that first. Since that part is very algorithmic, at least, right? There's nothing really to determine and to figure out. It's kind of just solve the equation. We know we have to take the areas or the equations of the curves and set them equal to each other. So we have square root of x equals 6 minus x. And then we just have to go through and do all the algebra. So x squared is 36 minus 12x plus x squared. Oop, 36. Brain's getting ahead of us. And then we've got x minus 9 and x minus 4 with this guy. So we get x equals 9 and x equals 4. And of course, as astute Calc 2 students, which solution do we want? This guy, and where did that solution come from? That is our extraneous solution that came from squaring both sides. It would have existed had I had this parabola continued down in the negative. So of course we want the x equals 4. That gives us our positive one. Looks like I didn't do too bad at just drawing that graph. So that should be over x equals 4. So we found our intersection point is x equals 4. However, when we do step 3, we want to do dx or dy. So how do we want to integrate this guy? Should we integrate with respect to x? Should we slice up vertical slices and have our width as dx, or should we slice up horizontal slices and do dy? Well, if we do dx,
horizontal slices,
yeah,
you don't have to worry about it being bounded by different things. It's always going to be bounded by those two equations.
exactly. So we always think in horizontal slices, it's going to be right minus left, and it's always the same. It's always this curve minus this curve. Whereas if we do vertical, it's going to be one function and then another function. Both methods will get you the correct answer. It's just that if we do integrate with respect to x, we would have to do two integrals. So for the sake of simplicity, let's choose dy. So dy works best. We want to slice things along the perpendicular to the y-axis. And so if we're slicing it up like that, our width of each of these slices is dy. What is the length of these slices? Let me use a different color here. Our length, whenever we're doing y, remember we want to do rightmost function minus the left, right? Our x, positive x is on the right, so it's always the highest in terms of our x minus the lowest. So right minus left. And so it's going to be y equals 6 minus x minus this curve. However, we do got to be mindful. When we decide our integral, our differential, that dictates what all of the variables have to be. So whenever we set up an integral now, all of the variables have to be y. We cannot have any x's. So we're in a little bit of a problem, not much, because, well, we found our intersection point is an x value. We want to be careful with that. Our y, and our equations were given in terms of y. So pretty basic. All we got to do is go back and do the work and solve everything for x as a function of y. So when we have y is equal to x square root of x, we get x equals y squared, and we will get x equals 6 minus y for our other equation. And so when we're setting up our integral, it's going to be the right minus the left. And now our right function is the straight line, so 6 minus y minus the left, y squared, dy. And then the bounds, what do we want to use? Remember, we've got dy, so everything has to be in terms of y, including the bounds. The bounds are going to be y values. So, and we always integrate in the positive direction along y. So start with the lowest y value, and we're cutting upward. So our lowest y value is 0. And then our highest y value is up here. Of course, we found the x value. How do we find the corresponding y value? I know that that intersection point, x equals 4, plug it into a y value, or into any of the equations to find the y value. So our y is going to be 2.
I have a quick question.
Yeah.
Do you have to redraw it if you do in terms of y, or you just go off of based off of the original graph?
Do you need to redraw it? No, I mean, if once you draw it, a good drawing is a good drawing. You don't have to like reorient anything or anything like that. Right? I mean, I drew the graph the first thing we did. Now that we're integrating with respect to y, I'm not going to redraw anything. We did actually mislabel things. I guess my drawing wasn't too accurate before I drew it. If you want to be a little more accurate with in terms of how you draw the graph, right? Our intersection point, this should be 2. So my tick marks, I kind of drew the graph before drawing my tick marks and should have done it the other way around if I wanted to be accurate. In any case, our upper bound for y is 2. And so this is our integral. And that one's pretty basic. Everyone should be able to integrate polynomial. I did want to do this example though, because it is one of these ones where we give you equations and you can't really tell just from the equations how we're going to integrate this and how we're going to set it up. So you do got to do a little bit of the visual drawing and geometry here. A lot of the other examples, sometimes it is just straightforward as to whether you're doing integrating with respect to x or integrating with respect to y.
Can you go back for just a second?
Oh, sorry, yeah.
Thank you.
Right, let's label that point as 2. It's 4, 2 on that point. Let's see. So I wrote down some other examples. I think these ones will be a little bit more straightforward. I did want to write them down and at least use some different functions. Polynomials are always the ones we start with. Of course, we've got our entire family of functions of trig and exponentials and logs that we can throw in these types of problems. So let's see. Bounded by y equals cosine of pi x and y equals 4x squared minus 1. So our graph, let's try to graph it a little more accurately. What's our period? It's going to be 2 pi over b. Which is 2. So if we were to draw cosine, our amplitude is just 1. And our period is 2. So let's make that 1 and let's make that guy a half. So cosine starts at a peak. It's going to come down. Do something like that. And that one's, of course, minus a half, minus 1. And then if we want to graph 4x squared minus 1, I know that, at least in vertex form, parabola is going to have its 0 at minus 1. What are the roots of this guy? If we took that and set it equal to 0, we get plus and minus a half. Nicely enough. So we know that the parabola is going to have roots here. And then we can graph that. Step 1, step 2, finding the intersection points. This is one of those ones where, well, what are the intersection points? Normally we would want to try to solve it, but we kind of already found the intersection points. How do we solve this equation? Can't solve by hand. But we saw x is plus and minus 1/2 graphically. So we saw the intersection points, both go through 1/2 0 and minus 1/2 0. Do we want to do dx or dy?
dx, since you could do top minus bottom.
Yeah, dx. This one's a straightforward. We have the equations solved for y already. And I can always do top minus bottom and get the same curve, or get the same two functions no matter where we're at. So our 3 and 4. We want to do dx, and so our area is top minus bottom. So our cosine of pi x minus 4x squared minus 1 dx. And then our bounds are from the intersection points we saw. Any questions? Let's see. Did we have any other ones? I had another one, but it was another polynomial. There's some with exponentials, but those are fairly straightforward in terms of integrating with dx and dy. I think it's pretty good for areas. This is one of those things that you just got to practice. And again, it is just graphing. So I don't know how much graphing you guys did in Calc 1. Hopefully you learned all of this in pre-calc and then did a lot more graphing with derivatives and slopes in Calc 1. So your at least intrinsic understanding of polynomials, trig functions, how the graphs look should be good enough to get you guys started. And then really it's just visually determining, you know, top minus bottom or right minus left, which works best for the shape that's formed by the intersection. Let's jump into volumes. It's a little more difficult, but it will build on this stuff. So we still have to graph functions and regions. And now what we're going to be doing is from these shapes that are formed between functions, we're going to be doing a very engineering type thing with them, and that's doing revolutions and extrusions in certain ways. So I don't know how many of you guys do any sort of like CAD drawings or anything like that, or if you're interested in that and thinking about getting into like MEs. If you're a mechanical engineer, you will for sure have to do some CAD courses. And a lot of the ways like computer design, when you design products, sometimes you draw like a 2D shape like we've been doing, and then you can do certain processes to now make it 3D. Namely, you can take shapes that you've built and rotate them. Like if we wanted to make a bowl or something out of a parabola, or you can do things like extruding, like making, you know, building just squares on top of a shape to sort of extend something out in an extra dimension. So this is kind of what we're going to get into with these volumes with various techniques. So I think the best way to get into some of these topics is to just kind of lead by examples. So this section, we're going to do volumes by revolution. So sort of subsection. Our technique is the washer disk method. We'll have 3 techniques for finding these volumes. The washer and disk method, there's going to be a cylindrical shell method, which we get to, I think, next Tuesday. And then there's these sort of extrusions that we make with cross-sectional shapes. That is kind of its own technique and kind of demands a bit of visualization out of you guys. It can be a little tricky. So we'll see how it goes. This method is perhaps the easiest one to start with. So the example we want to lead by is, let's do something basic. Find the volume of the solid obtained by rotating the function y equals square root of x, and we'll say from 0 to 2 around the x-axis. So similar steps apply. We've got a visualization problem. Not quite a word problem, but it is, there's some words there in terms of what we need to do with a shape. So it's kind of like a baby word problem in some sense. So we are doing visualization volumes, drawing a picture. It's always going to be a good first step. And we'll see if we need to add any extra steps for these types of problems for volumes. I'm not sure if we will. So let's see what we're working with. We've got from 0 to 2, so I'm only going to draw the right side of the graph. Y equals square root of x, so fairly basic function we're starting with. And let's draw it a little more accurate. So there's our function, and we are stopping at 4. Oh, I did write 2. I'll say 0 to 4 is where we want. 4 is a nice number to take a square root of. And then what are we doing? So we're taking this parabola, this piece of the parabola, or sideways parabola, and we are rotating it about the x-axis. So what we're going to have is this cone shape, this parabolic cone. And we have rotated it about the axis. And so we want to find the volume of this thing. So how do we do something like that? If we want to keep the same steps in terms of our bounds of integration, they are given to us. In our previous examples, if you skip, you can put step 2 or 3 at the end if you want. Sometimes it helps to find the integration and intersection points first. Sometimes it's easy enough to set up the integral and then find the intersection points, which will dictate the bounds of integration for you. You can do that at the end. So let's just get that out of the way. And then now we can talk about, well, how do we actually find a volume like this? Well, kind of similar to how we do areas, and this is going to be similar to how we do everything for the rest of the semester in terms of integrating and applications of integration, is we want to slice the problem up, or slice the thing we're trying to find, slice it up into small pieces and then add them all together. That is our fundamental process of integration. That's our big principle we're going to be using almost all semester. So generically, I'm going to start writing down some generic notation. Volume is the integral of dV. What do we mean by that? Let's see, where did my, there we go. This is just an infinitesimal volume slice. We know we're working or looking for volume in this case. Later we'll get into work, pressure, forces, things like that. Well, okay, so now I need to find an infinitesimal slice of volume. Okay, well, if we want to slice this thing up, cut it up in some way, shape, or form where I can measure infinitesimal pieces of volume, well, there's some advanced ways to do it in Calc 3. At the moment, we kind of want to build on the techniques we were doing for areas. Namely, we want to either slice vertically or slice horizontally. And so that way we can integrate with respect to dx or dy. So if we were to kind of just look at the shape we have as an area, do we want to integrate top to bottom or left to right? Do we want to integrate with respect to dx or dy? Which one would make better sense for an area? Top and bottom. Yeah, someone mentioned in the chat. Good. Exactly. If I do top minus bottom, we always have the same thing. Right minus left isn't going to work. So what we do is we cut it up, and each of these will have a infinitesimal width. The other reason we want to integrate with respect to dx is, as we see, let me draw this dash since it goes back. When we cut up with respect to the x-axis, we're cutting it up perpendicular to the axis of rotation. And when we cut it up in such a way, the width, of course, nicely enough, is just dx. But then the shapes is just a nice little disc. It is a cylinder, right? It's a cylinder with a tiny, tiny width or a height, depending on how you're oriented. I guess we should call that the height of the cylinder. And what is the volume in this case? So it is a tiny little piece of our cylinder. That is our dV. That is our infinitesimal piece of volume that we want to add up all of these tiny pieces from. And, well, the volume of a disk is pi r squared times the height, or excuse me, the volume of a cylinder, pi r squared times the height. And as we mentioned, the height is dx. So we're getting a little closer now. The dx is encoding our differential. We now just have to figure out, well, what is the radius of each of these disks?
F of x, isn't it?
Yeah, that'll be our function. So let's go through this. And actually, I'm going to write this as A times dx, where A is the cross-sectional area. Pi r squared, of course, is the area of one of the faces there. So our volume was the area times dx. We know we have our area there. And our area was given by, in this case, pi r squared dx. And now we need to figure out what our r is. Once we know our differential, just like in the last section, we know all of the variables have to match that. We have to have everything in terms of x. So we need r as a function of x. And we notice that for any given x value, since we're slicing up along the x-axis, we're walking along the x-axis, what is the radius we're hitting? We see that we're hitting the function that defines that curve. So r of x is just going to be our function, which is square root of x. So if we wanted to write down a formula for this, we've essentially arrived at the volume is going to be the integral from the bounds of pi f of x squared dx. This is, of course, rotated along the x-axis. It's going to be slightly different. We're going to have different axes of rotation. We're going to have intersections of functions, some funky shapes. So we'll see how this changes as we do more examples. So that's our basic setup, and that's kind of the general idea, general theory behind what's going on this. Any questions so far? So now the rest is to just set things up and do it. So we've sort of derived abstractly our formula, and we know we have a concrete example sort of motivating all this. So we want the integral of pi. Our function was square root of x. And yeah, dx is our h. And then our bounds were from 0 to 4. And of course, this is an easy enough integral to do. So I'll leave that to you guys. So in terms of our steps, our bounds of integration were here. Our differential was essentially here. We know that v is equal to dv. I kind of like to write this up sometimes for whatever calc problem. Just it kind of guides my thought process of what we need to find next. So this was our step 3, figuring out whether we're cutting up with respect to dx or dy here. And then of course setting it up and integrating was our step here. Okay, so let's see some more examples. Derive the formula for volume of a sphere. What's the volume of the sphere? Anyone know the formula?
4/3 pi r or pi cubed. Yeah.
Yes, sir. Pi r cubed. Yes.
Yeah. Sorry.
Where does this come from? So let's try to derive it now. We've got the tools to do so. Let's give ourselves some coordinates and draw our sphere. see how well we can draw a perfect circle here. Looks like we've got some oblongness. It's gonna happen. So draw yourself a sphere. Looks like this side needs to come down. Something like that. So here's our sphere. We know it's a radius r, and gonna be a sphere. So we'll draw some guides there. What's our equation if we wanted to model our top function? Hopefully everyone remembers equations of spheres. And how can we obtain a sphere now from this function? Of course, I drew the sphere already, but we want to use this process of rotation. So if we just think of it as a 2D graph, this is just the top half of a circle, right? What do we need to do with the top half of a circle to get a sphere? Let's do the same technique and rotate about the x-axis. Namely, if I take this top half of the sphere and rotate it this way, we end up with a sphere. And since we're rotating about the x-axis, we want to slice along the x-axis. Meaning, we're going to use dx. We'll generalize this once we see some more examples. Typically, whatever the axis of rotation is that you're going to use, you're going to slice perpendicular to that. As we saw in the previous example, it made nice little cross-sectional areas in terms of these disks. And so we can always use the disk method when we're rotating about an axis and we slice perpendicular to it. So we're slicing vertically. And so our slices are going to look like this. And of course, as we slice, they're going to get smaller as we get closer to our endpoints. Our width is dx. As we can see from our visual now, what are the bounds? The bounds are always where the slices lie. I'm going to make this note. I'll probably write that down again and emphasize that a little bit more. I don't know if it'll be too tricky for you guys in this section. I know once we get to work problems, it can get a little tricky. A lot of students it's easy to confuse what your bounds are in a lot of these physics and application problems. So just always remember wherever the slices lie, those are going to be what define your bounds. So our bounds are going to go from minus r to r, right? And they need to be x values since we've determined that we're going to be using dx. And so our integral, let's go ahead and set this up. And again, if it helps, we're taking our dv's, which is going to be the areas, and we determine that we're integrating with respect to x. This will help, especially once we're doing more different volume techniques. Sometimes doing these first steps help. And then now all we have to ask is, what is our area? And we've only known one method, so our area is going to be the area of these disks. So just pi r squared or pi f of x squared dx. And so plugging this in, we'll pull out the pi. I'm going to go ahead and put in the bounds to minus r to r. And our f of x squared is going to be r squared minus x squared. Square root of that squared dx. We get an easy enough integral. We can go through this one. I'll do it fairly quickly. Minus r to r squared minus x squared. Forgive me. My hands are getting a little shaky. All that coffee is hitting me now. The morning caffeine, get you going. All right, so we integrate. We've got r squared. We're integrating with respect to x. So r squared x minus 1/3 x cubed from minus r to r. And what do we get when we plug in? So we've got pi. We'll have an r cubed minus 1/3 r cubed minus negative r cubed minus 1/3 negative r cubed. And so what are we going to get? So we're going to get pi. This will be 2/3 r cubed. This will be a negative 2/3 r cubed, or negative again. So negative, positive 2/3 r cubed. And of course, 2/3 and 2/3 gives us our 4/3 r cubed. So that is the volume of a cube. So now all of these formulas that you needed
That's
to remember.
definitely not a cube. That's more spherical, I think.
Yeah. This will be.
You said it was the volume of a cube.
Is that what I said?
Yeah, you said now I have the volume of a cube.
Oh, sorry, volume of a sphere. I'm tripping on my words. So now all of these 3D shapes, I think in Calc 1, hopefully you guys did a lot of word problems. I know in the math department we do, where cylinders come up a ton, or cylinders or cones come up a lot. How many of you guys remember the volume of a cone from some Calc 1 word
Isn't it
problem?
1/3 pi r
Yeah.
cubed?
1/3 pi r squared times the height. Yeah.
R squared h, yeah.
But all of these formulas now for some of these basic 3D shapes, especially if they are rotated, you can now try to derive them and figure them out yourselves. And once we get to cross sections, we'll be able to do even more. Okay, so it's 10:30. Let's take a little break, and then we'll do a couple more of these, and then go from there. Yeah, time to derive volume of a cube. Yeah, you can do that now. All right, let's take a break. Let's do 5 minutes and come back at 10:30. Okay. So we want to generalize this technique, and we're going to see now what happens when we have some of these more wonky looking areas, and especially when we rotate them. And so let's do a rotation about the y-axis. It'll give us a different differential to integrate with respect to. So we want to find the volume. Solid obtained by rotating the area bounded by y equals x and y equals x squared about the y-axis. So far, easy functions. We are rotating about the y-axis. We know that x squared is going to be a positive function, so I'm just going to draw the top half of our graph of the plane here. So, of course, we've got y equals x. And then we've got y equals x squared. So perhaps I probably should have left more space for that. Yeah, let me draw this differently. Of course, the intersection point is going to be right here at 1. That's a bad graph. Let's give ourselves some more space. We don't need so many tick marks. We only need 1. So 1 and then x squared, of course, going to be a parabola. So that is our area. And now we're going to rotate this around the y-axis. So we're going to get our symmetry over here. See how well that looks. It's halfway decent. And now what's going to happen when we rotate this? Well, at the very top, it's just kind of like this thin point that's going down. But then everywhere else, we still kind of have these discs, except what happened, we cut the middle out of them. So this is what we call the washer method. Instead of a solid disc, we have these washers. So hopefully you guys can see that. Probably could have used a different color. And they have this gap in the middle. So I don't know what would make better sense to shade, make it visually, probably the actual washer. Where our width or our height of the washer is dy. So that tells us we are integrating with respect to dy. And I guess we should have mentioned, of course, our axis of rotation was the y-axis. So naturally, I already started slicing perpendicular to that, giving us that dy. And so now the same process really applies. Our volume is the integral of dv, but our dv is the area or volume of a washer. Again, volume of the washer, since we have just a linear direction in one coordinate, namely our vertical coordinate, is just a dy. It's going to be the cross-sectional area times dy, just like we did with the cylinder. And now what we have to do is figure out, well, what is this cross-sectional area in this case? The cross-sectional area is just, well, it's a circle, but with a circle cut out of it. So what do we want to do? Let me kind of bleed into the graph here for our derivation work. Our area, well, it's going to be pi times the outer radius squared is the area of that big circle. And then if we cut out the middle, we cut out pi little r squared. And of course, we can reduce that to pi times big R squared minus little r squared, where little r comes out to here. Big R, let me do that one in orange. See if that stands out enough. Yeah. Big R is our outer radius. So in breaking down our formula, in terms of what we are trying to find, we can pull out our pi, our big R squared minus little r squared dy. This, again, you can take as a generic formula for our washer method. If we wanted to now figure out, well, what comes next? What do we need to know? dy dictates we got to find everything in terms of y. So that means I need to figure out what this r is in terms of y and what the little r is in terms of y. So the big R is going to be the rightmost function. And of course, little r is our left function. So big R, we're going from 0 up to the parabola. And here, let's put big R, let's put a colon. We want to use the parabola, but what's wrong with the parabola in the current form is that it is solved for x, or excuse me, solved for y. We need to solve for x because we need the function in terms of y. So x equals square root of y. So our big R as a function of x, excuse me, as a function of y, we are integrating with respect to y, gives us square root of y. Likewise, our little r, easy enough, symmetric. So our little r of y, I keep doing that. And now plug everything in. So our volume is the integral big R squared, so square root of y squared minus little r squared y squared dy. We've got that pi out front, and we haven't found the bounds yet. So again, as I was kind of saying, sometimes you find the bounds first if you want to, or you can set up the integral first, find the bounds later. Bounds, easily enough, are where the y values lie. So our y starts lowest down here at 0, all the way up to, hopefully everyone knows that the intersection of y equals x and y equals x squared are 0 and 1. And those are the y coordinates for those y values of those intersection points. Of course, the x values are the same, but they're not always going to be like that for each problem.
So is when you do the washer method, is it always dy or just this example?
Just this example. So we could have taken the same shape, right? We only started with this area between square root of x and y equals x, or x squared and y equals x. We could have rotated that about the x-axis, and it would give us washers again. So let's see. We've got a few more examples. We can go through that example, rotated about the y-axis.
Basically, with both of these things, it very much depends on what axis you rotate around. So we have that volume at the top there, but you could also have a sort of sideways volume, if you could think about it like that, going around the x-axis, and then it's slightly different, the equations, because of that.
Yep. I've got a bunch of different functions to work with, and all of these we can rotate about various axes. Let's do, for the sake of simplicity, let's work with the same functions and rotate about a different axis. So instead of, let's do another dx one, but rotate it about a non-trivial axis. So we've got y equals x squared again. And let's say rotated about y equals 1. So we've got same function, same shape we're starting with. That's our area. But we're rotating it about not one of the axes, about a line, about a horizontal line. Y equals 1. So here's our y equals 1 line. That is our axis of rotation now, which means I'm taking this guy and sort of, it's going to pivot here and then rotate around this way. And so we're going to get a shape that looks like this. And then we are rotating about y equals 1. And again, we're going to slice perpendicular to the axis of rotation. So we've got vertical slices. The width of each slice is again dx. So again, general rule, we slice perpendicular to the axis of rotation. Which dictates our differential. In this case is dx. And generally you can kind of think of it, it's a little bit opposite, right? If our axis of rotation is a function of y, so the x-axis is y equals 0, y equals 1, we could do y equals 2, we could do y equals minus 1. So if it's y equals something, it's a horizontal line. Perpendicular to that will give us dx's. Conversely, in the last example, we had the y-axis, which is x equals 0. We could rotate about x equals 1, x equals 2, any x value. That would give us a vertical axis of rotation, which means we would then slice up horizontally along the y-axis, giving us dy. So our volume here again we want to use the washer method. We've got our cross-sectional area pretty clear as washers. We know it's going to be big R squared minus little r squared, where, and since this case we're doing dx, big R is our top function, little r is our bottom function. Those words are a little, may not be the best descriptives, because this function here we might consider as our top, quote unquote, but it's not really
Maybe like inner and outer,
That's
if you're
exactly
thinking
what I was
of
going
a
to say.
washer.
Yeah, it's really the top. Really, it's the furthest from the axis. And I mean furthest vertically. And bottom, the closest to the axis. Vertically. Change the words vertically to horizontally if we're slicing in the other direction. Or, as was mentioned, the inner radius, or the inner function, and the outer function. So it's, even that isn't the best descriptive terms, because it's not a function, top minus bottom. I guess we should say it's the distance. Here, let's actually add, I can put my quotes in there. Let's say the distance furthest from the axis vertically, and the distance closest to the axis vertically for our inner radius. And so why do I say that? Because it's not as simple in this case as just plugging in a function. As soon as we change our axes from, if it's not one of the coordinate axes, we can't just plug in the function, because we've in some sense shifted how we're referencing these functions. Our axis of rotation isn't one of the coordinates that define the functions. So let's take a look. Let's take a look at big R. So big R, we start at the axis and we walk, let's say, down to, where do we walk? Which function is furthest away? The parabola. That's kind of verbally what we're doing, right? Our distance, we would walk from here all the way down to here to find that distance. So how do we find the distance between two curves or two functions? Well, we've got this distance here. Let's actually use some colors here. So let's draw a little line here. This distance is our big R squared, right? What is this distance here? This, well, it's just from the x-axis up. That is a y value.
So why is that distance r squared and not just r?
Sorry, just r. Yeah, thank you. That is our r. This distance here is just y, right? We're walking up, that's a y value. But we know we're walking up to hitting that function, which is x squared. So this vertical distance here is x squared. We want this r value, and the total distance here is 1. So what does that mean? R has to be, is going to be 1 minus x squared. In other words, we can find this distance here. If we were to walk all the way down, there'd be a distance of 1, and then walk back, x squared would be right there. So 1 minus x squared gives us this outer radius. Likewise, for the inner radius, we can do the same thing. Our inner radius might be out of space here. Maybe we can draw it on the other side, might be easiest. Again, we have this total distance here is 1. The axis of rotation to the axis here, to the axis that defines our equations, right? We're defining things in terms of x. And then this distance is just x. And so our little r here is going to be 1 minus x. I don't know if I can get all that on screen. Everyone got it? And so now we can write down the integral. We've got all of our pieces. And this is how I often organize my work, because there are, you've got to figure out what dv is, and then we can break down dv. It's easier to find one piece at a time. Try not to get lost in the forest amongst the trees, or lose sight of the forest amongst the trees, right? Sometimes you can get lost finding each piece. Sometimes it's a bit of calculation, a bit of drawing, a bit of geometry. And then you kind of have to take a step back. Okay, how do we use these pieces? Which is why I like to keep my formulas organized. We know we're here in terms of our volume integral. We found our pieces, our r's were the last step we needed. And so now we can write it down. Our volume is going to be pi. Our big R squared, 1 minus x squared. Mind your parentheses. Another common mistake I see. Since our big R is 1 minus x squared, we're going to have an x to the 4th here once we square that term. And then minus the inner radius, 1 minus x, quantity squared, dx. And then what are our bounds? Our bounds are our x bounds. So x equals 0 and x equals 1 are where these slices lie. So we're going to integrate from 0 to 1. Any questions?
I actually have one. It's not so much about the washer method, but since volume is the integral of area and area is the integral of a function, couldn't you just do like the second integral of a function to get the volume of the function?
What do you mean by
Problem is you don't know what the constant is from the first integration. So that becomes your issue. So if you're taking like a line, if you imagine it's like one dimensional, you integrate it, you would get like an area. But the problem is you don't know what the extra constant is from integrating. So I guess you wouldn't know like maybe the length of the area. So you can't then take that integrated again. I mean, you can, but you'll have some constants there which you won't be able to resolve.
Well, that's one thought process. In some sense, you don't need the constants if you do it correctly, because we don't have constants here because we have definite bounds, right? So the question was kind of like, can we integrate along one direction to get an area, and then integrate along the other direction to get the volume? And the answer is, yeah, absolutely you can. And you're going to do that if you got to take Calc 3. So those are what's called double integrals. And it's essentially, you can do it more with a lot more complicated shapes, right? If we think of the volume of a sphere or the volume of any sort of 3D shape, instead of slicing it up into nice slices that have these nice geometric shapes, often what you do in Calc 3 is cut things up into just cubes and stack your cubes into whatever shape you want. And so there's an entire process to go about in doing that. So that's something you guys will get to. For now, we're kind of babying you into it, easing you into it a little bit with some nice shapes and still using our Calc 2 methods of integration. Other questions?
Could you go back to the previous page? I wasn't able to write the paragraph fast enough.
Sure. Let me go ahead and stop recording here.